There's two types of mirrors in general, plane mirrors and spherical mirrors. Plane mirrors are flat. Spherical mirrors can be either concave or convex. Now, plane mirrors are great because they give us a clear, non-magnified view of the object. Check out Army Guy in the plane mirror on this makeup mirror. He's very clear and non-magnified. But check him out on the concave side of the makeup mirror. He's huge. If you have this diagram all set up, then we're ready to go. Well, we've been messing a lot with ray diagrams. We've used several demonstrations to illustrate the idea of where images are formed. Well, it's now time for us to take this and start getting a little bit more solid information on being able to predict where an image is and its properties. We'll begin with the term of magnification. Now, we began by defining magnification back in our lesson on reflection. So I want you to recall that we defined magnification as the ratio of the image height to the object height. Image height to object height. And you know what? Image height we can abbreviate as h sub I over h sub O. Okay, now image height is one that was not on our diagram, so we best do that right now. Well, here's the image, and the height of the image will be labeled as h sub I. Now that's pretty logical. And the other part of it is this. Notice that we left this as a positive h sub O for an object that was standing upright. Well, our image is definitely upside down here, and we're going to throw a negative sign out front of it to indicate that that image is inverted. So we're going to use the symbol h sub I to mean image height. Okay, and the negative sign we'll just throw in right now indicates that the image is inverted. Okay, so we have a couple more pieces in place. Now, we've formerly defined the magnification as being the ratio of the heights. Well, we can also express the magnification in terms of the location of both the image and the object. To do that, we're going to look at a couple triangles. Two triangles to be exact. Now, there's two sets of triangles that we're going to utilize. The first set of triangles will be using theta. Now let's gain an understanding of the theta triangle so that we can convert our magnification expression in terms of height to one of distances. Now we're first going to look at the triangle that involves theta. Now this is the incident angle for the second ray that goes to the mirror and then reflects down at theta r. So these two angles are equal to each other. Now our first triangle will be from the object down to the mirror at this angle theta relative to the principal axis. So that is a very big triangle. So one more time, for the triangle from the top of the object to the mirror and back along the principal axis to the object. That's going to be our triangle. Now, if we want to relate the object height to the object distance, then the trigonometric relationship that does that is the tangent of theta. So our first piece of information here will be, let's see here. Let's use big theta angle. All right, we'll communicate that as the big theta, not angle, triangle. Big theta triangle. Okay? All right. So we're going to communicate the tangent of theta on that triangle. Well, tangent is the opposite over the adjacent. So if this is theta, then this is the side opposite that angle, so HO, and DO is the adjacent side to this angle. Okay, so tangent of theta will be HO to DO. HO to DO. All right, very good. Now let's look at the image. We've been using the object to get the change of from object height to object distance. Now we need to convert image height to image distance. So that triangle is going to be this one. Okay, it starts at the object, goes along this reflected ray, and back along the principal axis. So you can see this little triangle right here. And again, we want to find the relationship between height and distance. And so again, we'll use tangent, where the side opposite theta is the negative height of image, and the side adjacent to theta is the image distance. So the tangent of theta here will be defined as the negative image height to the image distance. Now this will be the, how about we call it the small theta triangle, okay, for the image. All right, well, we have gotten to a point where we define magnification as the ratio of the image height to the object height. So if we rearrange these statements to include these two terms right here, the height of the object and the height of the image, we can rearrange and solve for those in terms of di and thetas, the tangents and the distances. So here, HO will be multiply both sides by the object distance, tangent of theta, and over here, multiply both sides by di, and don't forget the negative sign. So HI will be negative di tangent of theta. Okay? So now we've got both of our object height and image height in terms of distances. Well, substituting them into our magnification expression, we end up with magnification equals HI over HO, which means negative di tangent of theta divided by do tangent of theta. And notice that the tangents of theta divide out, and we're left with a definition of magnification, not only in terms of the heights, but also the distances. So this is another way to define magnification, where magnification is the ratio of the image height to the object height. Magnification is also defined as the negative of the image distance to the object distance. And once again, recall that the negative sign here indicates that the image will be inverted. That's all it means. And you know what? Let's move that negative sign. Let's move that negative sign out here. That's where you'll normally see it. Okay? So we have the ratio of the image height to object height equals the negative ratio of the image distance to the object distance. Well, this is a really handy way to define magnification, because now we're using a little bit more of the information associated with our diagrams and what we know physically to be true from our observations. Well, let's use the other two triangles, the triangles that involve our angle alpha. Now, this will help us define what's called the mirror equation. Now, the mirror equation is a very handy equation because it enables us to say, hey, I have an object and I know where the image needs to be. How big must the mirror be from a radius of curvature point of view? So let's next go and define the mirror equation.